Okay. I think it's time. We will start with you. Good afternoon, everybody. I hope we will have a good time with this lecture. We are at Software Engineering Principles for Complex Systems. This is Lecture 8, Modularity. We will have a series of 2 lectures in this regard. And we will go through the first part of this, and I'm planning to introduce to you the issues related to the concept of modularity, especially with regard to software product lines. And then I will go through 3 distinctive parts of this lecture. One, to introduce frameworks and how they contribute to modular design. Then we will go through the application programming interface as a modular design concept. And we end the bulk of this lecture talking about concerns that drive design modularity. Let me first go through some concepts to make sure that we have the same language on terms. The issue with modularity is an issue of separation of the modules that constitute your software system into distinctive, independent parts, whether they are classes or features or modules or frameworks, to make sure that we are having a better ability to do traceability, testability, and reusability, extensibility, deliverability, and all the ATs that you might think of, because they are truly are consequence of good modular design for your software and hardware even system. So in short, in modular programming, we seek to have independent, interchangeable modules, and where our classes and frameworks are used to contain everything internally and abstract to the user of these modules what is internal to these components, to make sure that they are reusable and you would not tamper with them for other users and other systems. But let's just answer this. Why do we need modularity to start with? Is it something that is to enhance the design, or it's a matter of working or dysfunctional system? Modularity is not an enhancement in your design. It's a must requirement if you are to develop a complex system, if you are to have reusable or extensible system. There are many issues related to modularity. It really reduces the problem and the pain areas that are related to many issues. At the top of them is reusability and extensibility. Reusability, you heard a lot about it. You have modules and features and classes that are going to be reused, especially in the area of feature being as a module. And through variability and configuration management, you need to produce products in the software product line. But extensibility is another concept that maybe we haven't talked a lot about it, but it is essentially very important in large systems. The aeronautical industry, the airplanes, and in the military, and in the auto industry, in the mobile industry, telecom, extensibility is very important aspect of developing a new generations of software and protecting the investment in the huge repositories of artifacts that these big companies do have. As one of the CEOs of big company was saying that extensibility is our insurance towards protecting our investment and our ability to roll out new product lines in a very short time, in very complex systems. Let's say in very strategic jet fighters, let's say there are softwares and things that are really not only extremely complex, but there are lots of issues related to trade secrets and the ability of people to see under the hood. And therefore, there are just limited number of engineers who are aware of the big picture. But especially groups in these systems, they just need to know the extensibility points in this software, and then they go and develop new products based on the fact that they deal with these as black boxes and they extend them. So the issue is not luxury, the issue is not enhancement, the issue is a matter of having it or not. Whether you are able to develop software products, be able to test them in time and deliver them on budget. The issue is important here. We talked maybe before about encapsulation, and this is one of the techniques that you do abstraction for your models, and you hide the details from the users so that it will be extendable and it will be reused all the time. It has to do with the grouping and packaging things to make things coherent with each other and putting things coherent in one package. And inheritance here is done by defining new classes as extension to existing ones. You use inheritance to avoid violating the principle of encapsulation. You use it to develop subclasses that will define by inheritance whatever you want to do, and then you can do modification and change to your subclasses. And just we want to make sure that we are on the same sync on cohesion. We want to separate the features in distinct artifacts. So in the artifacts that you are developing in software product lines, you want to make sure that these features are separated into distinct coherent software, not only that it is decoupled and it's modular, but also this cohesion that would help people be able to trace, be able to audit, be able to understand and debug the systems. The issue of variability is very important, and it relates directly to modularity. If you want to be able to do variation management for your artifacts or for your features, then it helps a lot and facilitate this practice to make sure that it's modular, and we are going to prevent in the design of variability the issue of cluttering software. We want to enhance the features traceability because you want to be able to know which belongs to what, and we want to be able to provide the extensibility that we want from existing artifacts. Also, we want to be able sometimes to extend this variability to do it in a static time or in compile time, and it depends on what is your objective in the design. In the previous lectures, there has been an introduction for design patterns and how they help us develop variability. In this lecture, my focus will be on frameworks and then about the design concerns for modularity. So let's dive in a little bit in the issue of frameworks. So the frameworks are abstracts. They really help us abstract a group of classes at a larger scale in a large granularity type of design and projects. You can think of them as a class or a method, but in a larger aspect, they could just abstract a whole software system, as we will see later in Eclipse. So frameworks can be sometimes treated like a black box, and then we use extension or hotspots, we call them plugins, to connect to. And we see this in let's say, browsers, like Google browser. You have these plugins that you can add extensions without getting into the details of the implementation of Google browser. Third-party companies can develop these frameworks and connect them after compiling without knowing anything about the other software except about the hotspots and the extensibility points where they can connect. So we say also a framework is responsible for the main control flow. It's not the host, it's like the opposite. This is called the inversion of control. As you know, in your main program, as you usually call functions and procedures and library things, but here it's the opposite. The framework is the one that call and do inversion control to execute functions on behalf of your program. So in that sense, we said that the framework is different from the library functions. It's in the area of the inversion of control. And the golden rule for a framework design is to write a plugin and an extension, like we said, and it should not require modification of the framework source code. So it's considered a black box. But we will talk about this black box, white box, and what's the difference between them. But what is, as far as we are concerned in this course, I think the black box is our target, but we need to explain the difference between them. And as I mentioned, we should have a flexible understanding of these frameworks because there are total systems that composed of maybe thousands of classes are still called frameworks. And they use the plugins, as I said. In integrated development environment, they are used a lot, like in Eclipse ID and Feature ID. Actually, also in a pure variant, for example, which is like Feature ID, it is a plugin. When it comes to Eclipse, you have a plugin for Feature ID, and you have a plugin for pure variants, and maybe you have a plugin for gears. All these tools connect to the system as a framework with a plugin. And as we said, these plugins are developed and compiled independently by third party. They don't need to know anything about the host software. They just need extensible point and the plugin. And the plugins industry is huge, and it's a very good way for collaboration between companies and adding functionality without disturbing the main line or software product line. So in that sense, we come to the point that feature-oriented product line development, when we have these features, would fit ideally in this plugin concept. So we develop one plugin, for example, per feature. Let's say you have a system that is good. Let's say consists of so many features or so many product lines, like a software product line, and you want to add or do extension for its features. So features can be designed as a plugin and configured the application for this, to assemble it and activate it as a plugin, which corresponds to this feature that you are adding to the system. Here, the issue of frameworks, white box frameworks or black box frameworks, it has to do with the extent the framework that override and adding methods to the subclass. In the implementation of white box framework, you need to know the extensions, the procedures, the methods that are inside the frameworks and do extension for them. So you need a prior knowledge of some of the code within the framework. And that's why we call it white box, because you have to engage and develop your extension through extending the methods inside the framework. So you need to understand the framework internals. However, and the black box, as we will see in this is why, for example, I'm saying white boxes frameworks are criticized for neglecting modularity. It has a violation of modularity because it has this issue of engaging the internals of the framework to develop extensions. On the contrary, the black box separate the framework code and extension in an abstraction model. And in that sense, the features are implemented in a separate plugin. So the whole framework is treated like a black box. And there are explicit hot spots where you plug in your extension to the framework. So we say that the interface internal implementation of the framework is unknown to the user, and therefore the name. Here, for example, we see the implementation of a black box framework. If you are to develop software that works with Mac OS or works with Windows or Androids, it's not feasible for you as a company to develop a software for each, but through a black box interface as a framework, you can then develop one software that will work with all OS systems through a translation mechanism, and you don't have to understand the details of Windows or AS. All what you need to know is about the plugin requirements and the hotspots that you need to connect to, and you are okay. If things will work as far as the user is concerned, they will feel nothing, they are operating. I think in that regard, for example, if you have a Mac or a book, you can run Microsoft Office on a window emulation, but in this sense, you can have maybe a software that will work on both of them if you have this a plugin that will do the interface for you. So in this diagram, I don't know where I can get the pointer here. Okay, anyway, I hope you can see the mouse. If you see here on the left, there is an implementation of the white box, and we are planning to reuse this module. And here in the white box, you are extending these methods down into like a procedure for button and close box. They are extension of what is internal to the framework, and therefore the name white box. And here, in the contrary, you are not going to touch this framework. It's like for you, it's a black box. All what you need to do is to have this extension that being created. It's like an aspect. We'll talk about it later. And from there, you develop whatever features and extensibility you want to do. All what you need to know about this, the plugin requirements, the hotspot that connects with the black box. That's what it means when it comes to black box framework. So in short, as a user, the black box is an abstract for you, and it's a black box, and all what you need to know is the plugin requirements. This would take us to the discussion about application programming interface as a usability tool. As we mentioned before, We are familiar with this in when we call a function or a procedure in, or even a class into a library. You make the inquiry and you get the execution, you get the data back. This is one way of avoiding duplicate or copying or cluttering your software. It's a neat way in object-oriented software to do this. But here, the APIs are a neat way also to refer to the functions and methods in the library. And there are even software development kit for that, to develop your APIs, which would enable you as a bridge to get all the functionalities and the classes and the procedures that you need to do with the library. So in short, API provides an abstracting functionality to the library. They are extremely important. All of you have used them. For any program you need API. It avoids the issue of duplication and entanglement with your code. And as we said, the APIs offer many benefits as well for modularity. It enables us to develop modular software, separation of concerns. We're going to talk about it in a while. Decoupling, definitely. And we have also ability to do information hiding and enhance testability. Testability is greatly enhanced with this decoupling. Also, traceability will benefit a lot from that. And all the above, it should be easier and simpler for us using API. Here, for example, you have ability to create a variation in your software. And this is the traditional way. If you have a single application, you clone and own, and you can make the library calls and get whatever modules you want. You get these components or frameworks from the library and use them. The way in also in software product line where you have assets and artifacts and you have configuration management here, you can still also get variations from your artifacts, from your component library, from your frameworks. But the issue here is more complex and enlarged. It's a complete project. Still the same way you can use APIs to create variants in your software and extension points. So we say that it's a good programming way to implement APIs because of modularity issues and because, of course, modularity is needed because of, we want reusable and extensible software. And the code quality will be improved a lot. We don't need to talk much about this because it's obvious. Your implementation should not be impacted using APIs because they are treated like black boxes for you. So you don't, if you have implementation details on APIs, you will confuse the user, you will violate the concept of decoupling, and you will have other issues. We will talk about them in a while. So implementation details are, we are talking with regard to API. Implementation details of API. So for example, specifying a hash function in your API is not recommended. And here we talk, don't let implementation details leak into APIs because APIs are supposed to be reusable artifacts and they are not supposed to be customized for any use case. You should minimize access to everything within the API, that you just access the model from outside as a black box. You make classes and members as private as possible. You don't want to make public classes as public fields. And you need to maximize information hiding, as we will talk about this principle later. Information should not be exposed to the interface, it should be private, and information hiding is always recommended. So all of these areas or allow models to be used, understood, built, tested, debugged independently are all recommendations when it comes to APIs. Also, we need to minimize class mutability. You cannot modify the instance in these classes because they should be immutable. Immutable in the sense that once they are built, nobody tamper with them and change them. They cannot be modified. The way to change or customize, we say through aspects or through subclasses or any other things. But classes should be immutable unless there is a very compressing and important reason to do otherwise. And the usability issue is at the top of the reasons why we want to do that. So, for example, when you refer to make a call for date and calendar, it's not a good practice. You just make a call for a model timer task, and this way you do not expose the internals of the model and violate the immutability principle in these classes. We say minimize, we don't say eliminate, because sometimes it's impossible to do that. Okay. We move now to the main half of the lecture, which is modularity drives. I just wonder if anybody has any comment or question. Let me look at the chat. Okay, what is that? Okay, just note that assignment 3 has, okay. There is, I think, a question about here. We mentioned that you need to minimize a class immutability in a sense that you don't want to expose the internals of the class to the outside world or make them public. So make it clear when it is legal to call which method. We're not saying that this is a violation of code, but we are saying it's not good practice to have a call of separate date and calendar. And instead, it is good to have timer task in a sense that you encapsulate or you abstract what you are calling, and instead of putting the internal of the class as part of your call and make the user of the class mingling or changing the internals of the class. And that's why we are saying that the internal instance cannot be modified, and therefore if they cannot be modified, then why you should call them specifically, or you should not have even a prior knowledge of that there is data, there is date and calendar to be called. Okay. By the way, before I forgot, the assignment 3 is out already, and you can start working on it. And but we just want to make sure that you finish with assignment 2. But for the sake of time, some of you might, or some members of your group, can start working on assignment 3 if you want to save some time. Okay. In this section, we will talk about modularity drivers. These are principles that would drive and motivate and encourage developers and designers to have modular design that would serve all the purposes that we mentioned about. And this is one of them, the layered architecture style. As you know, and even in design patterns, all of these design patterns were developed to encourage also modularity and decoupling. So here in this example for web portal, you have here in this web application, the user layer distinguished, separated here in red color. And you have then the business logic in this layer design, as you know, comes in the middle, the application layer. And then here you have the persistent layer, the data access layer, and whatever infrastructure followed to access your data and database. So what we are saying here, in a layer design, it helps you distribute the roles and responsibilities. So when you have specific roles, we say here are users, here are application logic and business logic, and here you have the database access. And this would help you really componentized your design, make it components and separate the concerns and enable you to design things as modules and achieve modularity doing so. So your presentation layer is very obvious, and application layer is also separated from the bottom layer, which is the, this is at the large picture. In the same way, service-oriented architecture, it does expose and consume the services that are available here. For example, here you have the users in service-oriented architecture. Then you define a layer of processes. We call it business process. Here you define your process workflow of what you want to achieve. And then you have here the services. These processes, they are like a workflow, and they call services like we said in like framework or classes. They call the services to execute their workflow and process. So in that sense, it is service-oriented. And here at the end, you have the logic and the data, the persistent layer. You have the enterprise service bus that coordinate between the services and the underlying layer of the infrastructure. For example, you have an infrastructure for CRM, you have infrastructure for mediation and for prepaid system, if you are like in telecom, or whatever it is, the business logic you have. You have an enterprise bus. It communicates with the services and provide them whatever data they want. And in that sense, we have separation here of layers. It's like the layer design, and it's very easy if you have this architecture to develop modular design by designing these services as modules, by designing these processes workflow as separate modules or frameworks, and so on. We say here service-oriented architecture codifies how we can publish, consume, and discover these services. So this is even the motivation behind service-oriented architecture was extensibility. You have a company that developed the engine, which we call it the service bus or the business bus. And every time you need to add a service, all what you need is to come to this layer here in the middle and add a service. Extensibility here is the big motivation behind this design. Let's talk about separation of concerns. The relationship between the features and corresponding design in implementing these artifacts should be explicit. Like you have one feature, let's say this feature is to distinguish certain image. We would be able to trace this feature and separate it as a function throughout the design and have a relationship. This has to do also with traceability. We'll talk about it soon. The separation of concern says that if you have a function, you'd better implement it in one module, in one feature, in one class. You cannot just split it and scatter it all over the place, and then you would have violated the separation of concern requirement. If you have extra functionalities, it says here extra modular unit, may be dedicated to encapsulate the functionalities providing data persistence. So if you have an issue with these concerns, you can just encapsulate them into one model that would carry all these concerns together rather than having them into separate models. And then you have you have mixed the concerns, the functionalities into single models, and that's not what we want to do. We want to avoid this situation. Separation of concerns. Features should be implemented in their distinct artifacts. And you should be able to trace these features, as we're going to talk about traceability. Related pieces of code should be implemented together, not in separate areas. So in service-oriented design can be separated. We can separate the concerns into classes and services. So you have classes, each class would take care of a concern or a function, and or each framework will take of a concern or function, but you don't put them together. You have to separate them. In procedural programming, of course, you can use procedures and functions to separate the concerns rather than classes and frameworks as in service-oriented design. So there is a way to improve the separation of concerns through what we call it dependencies by injection. In injection, we inject the model that wants to have functionalities without being connected to another module, and then we have mixed of concerns. If there is a module that has achieved separation of concern, but it requires additional functionalities, we do it through injection. So this model becomes a client that wants the service, and the injected code is called the service. So in that sense, the injection would refer to passing this code to of a dependency. We pass this code as a service, and the object receiving this code would be called the client. So injection would help us achieve the separation of concern by using these injection procedures. We will show this here in more details. You will see here, for example, a client that has some dependency from a service. If this client would depend on its execution on this service, we will say it is tightly coupled. If it is tightly coupled, it violates the principle of modularity. And it's difficult to have reusability for this because of this instance, because of the violation of the abstraction principle. And in that sense, we will have a problem. So the injection here, what it does is introducing this injector class. And when it requires some dependency from these services, it goes through a broker. Let's call this as a broker. It's an injector class. It will take the request, inject it into these services, and these services will implement it in the service interface. And here we call it soft dependency because it's temporal and it does not violate the abstraction of this client class. This is done dynamically by dynamically load and return the implementation class through here. So in that sense, the injection procedure allowed us to avoid this situation by introducing a broker here. Like we saw in other design patterns, we always introduce a broker like subclass or encapsulated subclass. Okay. know, maybe we will take after this little break and come back. The cross-cutting concerns, it's about how difficult it is to have concerns like little things in different models scattered left and right, and they are difficult to separate, usually inherently difficult to separate. So we need to make such separation of concerns to simplify design, evolution, and ease of maintenance. We have certain codes, we call it a cross-cutting, like logging, like security issues, like other functions that are implemented into different classes, and it's difficult to extract it and abstract it and make it available. So there is a difficulty to map it into a single class in simple. So what do we do with this? In object-oriented programming, there is a solution for cross-cutting concerns is by implementing the aspects. So the aspect is a modular unit that cross-cut the structure of other units. And the aspect is like a broker. There are elements such as security and synchronization issues, optimization, communication, integrity rules that are always used across traditional model boundaries. Some of them implement I/O and other functions. So you need to implement all of these in a separate model. We call it aspect. Therefore, you will not have this cross-cutting concern. As you see here in the example, you have here the cross-cutting issues available in subsystem 2, subsystem 3, and so on everywhere. So you need to standardize this. In aspect-oriented programming, you have a mechanism of creating what's so-called the aspect. For example, for subclass subsystem layer here, you create aspect 1, where you can move all these cross-cutting codes into the aspect. And this way, these elements become reusable and extensible easy. And this is how you do it, like we did it with injection. You have aspect 1, aspect 2, aspect 3, and so on, as many as you want. And you localize the expression of a cross concern. It becomes only here as an abstract, and it's not in every different subsystem that would make it or violate the modularity of these subsystems. Okay. Let's take 10, 15, maybe 15 minutes, I would say. I will look at your chat, and we can come back. We have the time to go over the rest of the material that deals with modularity drivers. And we'll see if anybody has something in the chat. Why are we casting the service? I don't know which one this refers to. If you can elaborate more, at what point casting the service? Casting or broadcasting? I'm not sure about the question. If somebody can elaborate more. Okay, when we come back, we'll see if there is more elaboration on this question. And we'll proceed with modular drivers. We'll take 15 minutes. Thank you. Okay, we are back. All right, the next thing about modularity drivers is the code tangling and scattering, which are actually manifestation of the cross-cutting concerns that we talked about. And we said in aspect-oriented programming that we use the aspects to deal with that. As you know, in object-oriented programming, we use classes, but in aspect-oriented, we enforce modularity with aspects. Now, these code tanglings and scattering will manifest themselves in like software product line. You have code related to tracing, code related to transactions, exceptions handling, and implementation of testing procedures or security procedures. And they are everywhere. They are tangled and scattered in every class, and in every single class, they are tangled into different areas of the software, and we need to deal with them. So in this regard, just to define things, that code tangling is in each class. It happens in a single class where you have methods for a tracing or a transaction or exception handling are tangled in different areas of the software and are not self-contained, where you can treat them as an abstract. So this is why we call them tangled code. And then you have the code scattering, which is involved in different classes or modules, where these concerns are everywhere. They are not implemented in a single specific unit that we can deal with. They are scattered all over the classes, as we see here in this diagram. As you see in these colored lines, we have code tangling for code related to tracing, transactions, exceptions, maybe security handling, or whatever procedure and methods are used here within the package class that causes the code to be tangled. And on the same token, scattering is to have these appearing in every class, everywhere. So this is the problem of exposing the internal of these classes to the outside world and force the developer to deal with it, and violating the modularity and separation of concern, information hiding, and decoupling of your classes or systems. So what we do, if we are dealing with aspect-oriented programming, the solution would be that to develop an aspect that takes care of all tracing code, and therefore you clear this code from these classes and make them abstract black boxes. Same token here, you take all transaction code and implement it in an aspect whereby you clear this tangled and scattered code from all over. And the same thing, you do it for any group of tangled code functionalities or methods. You just implement them in an aspect. And therefore, your system becomes clear of all these cross concerns and tangled, scattered software, and the problem is solved. Information hiding is also another concern, that you want to achieve this information hiding to distinguish between what is internal and what's external to the module. Internal part would remain hidden. You need to hide the internal part of the module and abstract it to the outside, so it's a black box. And you need to expose the things that are not part of this module outside into a different module, like we just did on the issue of aspects, entangled and scattered code. And we say when the features need to be separated, We also hide internals of their implementation and make all communication between them explicit on the interface side. This is, we talk about features that, let's say, feature is implemented within a class. Same thing will go for the class. You want to do information hiding. Therefore, these features that you are creating in software product line would become reusable and extensible by respecting the modularity, and therefore they are decoupled, and you can implement all these variations and extension and configuration management on them to create new products. So here it says that you do information hiding by encapsulation, and then you extend these to implement details to the system. So encapsulation being abstracted interface, like we said, when you encapsulate a model, you abstract it as a black box. And that's what you should be doing. The big issue here about reusability, and as we mentioned before, modularity is geared by two major objectives. One is, we said, reusability, and the second one we said extensibility. Reusability is your ability to use the feature or the model as is without modification, unless you want to modify through injection or aspect or interface broker, that's fine. But this is the reusability concern. And we mentioned before about extensibility. Extensibility is to allow you to, yes, use the model or the feature, but in addition to that, another requirement is that you want to extend its functionality. You want to use it, but you want to create an extended feature that would be a different feature than the one that you are using by adding more software, more functionality to it. But you want to make sure that's been designed to be extensible. As I said, in large companies, this issue is very pressing. When companies spend millions and millions in their software and they don't want to reinvent the wheel, yes, reusability is there, but when they have a new systems, the new models, the new technology, they have to use the existing artifacts, but with modification by adding extensibility. Now, when we say modification, we don't mean to break the rules of modularity, wide open the module or the feature and tamper with it. They don't want that. They want to keep their artifacts, at the same time provide extensibility point where you can, it's like the plugin, where you can add and modify to satisfy the new requirements of the new system. So to satisfy reusability, we said we need to do modularization, and we emphasize this point more on time. And we said that modularity and reusabilities are like two faces to the same coin. The second thing that would support reusability is cohesion, and cohesion here helps engineers understand the artifact, understand the feature, understand it's a cleaner code. They can identify, they can do variability management properly, and they are able to deal with abstracts of classes and models, and therefore they are able to reuse it in much faster time and cost. The third one is loose coupling, and we talked about coupling a lot. If you want reusability, the system should not be connected directly to outside world. These modules and classes should not have any association directly and expose their internal to the outside world. But we always said we use these brokers, whether it's aspects, injection, and there were other design patterns explained in the previous lectures to avoid this dealing directly with the outside world and get exposed. It's like a middleman. You just expose yourself to the middleman, but the middleman doesn't expose you, and it deals with the outside world, so you don't have this direct exposure. Also, to be realistic, we are not assuming here that the decoupling is going to be achieved 100%. Like you have zero coupling, this is impossible. Sometimes you have to have a level of acceptable coupling that programmers understand and can deal with without any confusion. And but high coupling, as we said, is the problem. But we are not calling for zero coupling because this is not practical. Okay. Again, on the usability concern, there is the issue of testability. And I think there was maybe a full lecture by Gregory on this issue. The testability issue is a big one because, as you know, in agile practices, and we will talk about this in the last lecture, in agile practices, you need to make sure that the continuous deployment and delivery and deployment in agile process is important. It's extremely important to be able to do continuous testing and incremental phase in each milestone. So testing methods and functions are important for reusability. You need to be able to separate the preconditions for testing. When you are testing these black boxes, you need to also understand the conditions under which you are testing, the circumstances, the interface, the environment, the functionality, and the stress type of testing you want to do. And there are testing by itself is the whole world of details. We can highlight some of it here, but we will not be able to. It requires different lectures. We need to be able to use divide and conquer in general for testing because it's a complex problem. You need to be able to isolate certain functionalities and test them. Therefore, modularity would help us a lot of divide and conquer and to a level that is acceptable, because testing can be an NP complete problem in terms of complexity. If you're trying to test a big part of functionalities, whether it's a static or dynamic testing, then you're going to have an issue with time frame. I remember in the past, at least at the level of integrated circuits, when they were trying to test a size, a chip of microprocessor, it used to take like 6 months, 7 months to test. And at that time, they were able maybe to wait that long. But nowadays, no company, especially in the big ones like Intel and Apple and others, would wait 6 months to test a system as complex as with billions and billions of transistors and things. But in software also, the problem is more complex because you have different types of testings that you need to implement, and you need to deliver a software that is acceptable. Let me give you an example here of the complexity of testing. In terms of overhead, you have like a 20% overhead on testing compared to the total development of a system. This is on a single software, single component application. We're not talking SPL here. When it comes to two components, two systems, two software systems that are combined, then the overhead jumps to 30%. When you are including the peripherals and the GUI and other issues, it jumps from 30. We are now at 1/3 of the cost of development is dedicated to testing. So testing is not a simple issue. Imagine if you have then a complex software product line. Of course, you don't test the whole product line at once. You're going to test it as single applications, but still the complexity of delivering an SPL that is bug-free, error-free, and completely tested is not a simple task. So the main idea of reusing the artifacts, which includes the software test set, you can think about the software that is testing the artifacts, whether it is a code or whatever it is, as an artifact, as a reusable element. Therefore, we want to design, let's say, a design set for testing and reuse this for different components with a minimal variations. This is the target of testability concern, because when you have your features designed as modules, and these modules have some similarities through variation and commonality analysis, then you will be able to test these common functions using the same test. And under variability, you will know what are the variants, and then adjust your software accordingly to do the testing on that. In that sense, there is what's so-called model-based testing, MBT technique, and it's proposed for software product lines. It is more efficient and possible to perform all these rigorous testing for the system. Let's talk about this MBT. MBT actually treats the circuit system under test, which we call it SAT, or circuit under test, we call it CUT. It's treating the SAT as a black box, which what we want when we deal with a complete decoupled module. We treat it as an abstract. We just expose the external I/O, and we understand what's the input, what's the output. From there, we treat it as a black box, and we develop our test set here through this module. This is the test model that we use, whether it's a software, a series of data, of testing data that we inject into our test case generator. This is a generator, which is another software that would take from the model, and the model would try to simulate the actual product under test and generate the test data. Then we use this data after applying an adapter and test back and forth all the things, whether it's stress testing, whether it's partial testing, which is complete testing, whether it's a static, we test the code before execution or compiling, or it's dynamic, we test the code as it executes and operate. And here you see a taxonomy, a hierarchy for the testing, and there are actually more complexity than this. You can divide your test set to a static and dynamic, and then you have here a black box, you have white box, and under the black box you have non-functional and functional, and I believe under the white box also you have functional and non-functional. Now, having said that, the issue related to functional and non-functional is also a big issue. It's like two worlds. When we deal with functional, the issue is maybe clear. We know what are the functions, and we're going to simulate them and test them. But non-functional is more tricky, because here you deal with analog parameters. Let's say we are testing the response time of a system, the performance of a system. We are testing certain features, let's say energy consumption, heat dissipation, and other things. Then the test here is under stress testing, and then you have lots of equipments involved, and it's getting messy. At any rate, we need to verify the code and validate the code of what we are testing, the SAT, system under test. If it is verification, it is for a static, most likely. If it is validation, if it is for dynamic code, most likely. Then we need to decide whether we're going to do black box testing or white box. Usually the client would define all these things for you, because the stakeholders at the end will define for you as an engineer what is constituting an acceptable test. And then we have to deal with another headache. It's called fault coverage, because testing has results, has KPIs. You cannot just test a system by saying go, no go, or accept, reject. This is not what it is, even in hardware or other than software. Usually tests come with so many benchmarks and KPIs. For example, if I talk about one KPI here, which is the fault coverage, how much you covered out of these faults based on your fault model. Let's say you have developed a fault model that simulate the software behavior and the performance. And you say when it reaches certain threshold, this is constitute a fault or reject. And then you define your software that will do the testing. And then you produce a fault coverage by telling the customer or your client that I have been able to test, let's say, and define and produce 90% fault coverage, which means if you have 100 fault, you were able through your test to catch 90% of these faults. That leaves the opportunity that there might be 10% of possible faults or defects that are not tested under your model. Now, usually under contract, these are things that are defined. I know, for example, in the military or the aviation, the accepted fault coverage is 99.999. So they will not let you give them 90% is just a joke. They will not accept anything, even 99 is not accepted. So some systems, critical aviation systems like space and jet fighters and others, they have like 5 nines in their reliability testing. And they want to make sure that they have done the exhaustive testing for every subsystem. The difficulty will be is to test compound systems and when they interact with each other, and that makes the problem extremely, extremely complex. It is 2 to the power n in complexity, where n are the points to be tested. Okay. Traceability. We here talk about understanding of the system variability. When you have your product line and you have a problem domain and a solution domain, you need to be able to trace forward and trace backward. If you pinpoint, let's say, a feature, you want to be able to find the product line that relate to this feature and take a code from product line, trace it backward to your feature, like maybe something close to what you're going to be doing in assignment 3, where you have these robots and you need to be able to trace back and forth from the code back to the features, from the features to the code, so that you can do your variability management and be able to isolate and understand the commonalities and the variabilities across these 2 domains, to understand which code belongs to which feature belongs to which code, and then your feature model would be clear to you of where the code is and how at the end you'll be able to create derivation and drive your derivation model to create a new product or a new robot. So we say that modular design supports traceability. We said this before, and reduce its complexity, definitely, and especially with large features. For example, if you have a system that has, let's say, F features, let's say for example, you have like 50 features, then the domain complexity will be 2 to the power 50. It's a huge. When you look to all combinations of variability that can be done and produced with this feature being present or absent. I'm not even talking about feature that is used in a different way. It's just accept or reject, include or exclude. If you just use this binary, yes or no on the feature, you are dealing with a complexity of a magnitude of 2 to the power f. So back to traceability. In traceability, you need to do mapping 1-to-1 of variability of features model between the problem space, as we mentioned, in domain engineering, to the solution space and domain solutions when you start developing your software product line. That's what traceability. I know there are several PhD research even in Chalmers and GU, about traceability in software. So it's not a simple, straightforward issue. It's a big issue, and many companies feel that traceability is a must capability in their systems to be able to design and develop. So here, for example, showing you a mapping between feature model and implementation in the solution domain. This is a problem domain, feature model, and this is solution domain when you start developing virtualization of your solution using containers. These are like containers, and you are virtualizing your solutions. These are like, you can think of them like a product line, consists of different functions and sub-functions or components. And you want to be able to move both ways from your feature model back all the way, this is forward tracing, to the solution domain where you can understand this product is composed of what features, and even be able to pinpoint to a feature and trace it back to the feature model. Same token goes backward. As I said, you can identify a feature in your system at the code level. Maybe here we see it at the implementation level. It's the same. These are all codes. You can come back and trace your feature at the code level all the way to the feature model. Why this is important? Of course, it's important because of variability design. When you want to do variability and the commonality, you come back to redesign your feature model. As you know, in any design effort, you start with the feature model and domain engineering. You develop your feature model. You realize it here in a solution after you do the selection of the variabilities and try to mix and match and develop your product. So design tools, automation tools like feature ID and pure variant or gears, all of them would help you develop these mapping processes, because when systems become large, it's crazy to do it manually. Okay, let's see if we have anything on the chat. It sounds easy to practice, but do you have concrete example on how to do it? Still, I'm not sure what was the early questions about why are we casting the service. If this question is elaborated further, so because it's a follow-up from the same person, from Emmanuel, it sounds easy to practice. Nothing is easy to practice, but we're trying just to introduce the concept. Wish if you can elaborate about what point casting the service, what area of my presentation that relate to this question. Anyway, maybe by the end we can handle this. But as I mentioned here, we need to relate the software artifacts to its corresponding design decisions. We need to understand what motivated a design decision. And then in the future, when we're trying to develop a new product, then the engineers understand why this decision was made, why this design was selected, why this software was developed, and everything is becoming clear. So when you come with the requirement of a new product, then life is easy. Okay, we say here in there was a module in pure variant. They call it family model. I think it fulfills this function that we just mentioned. It relates the features, feature model to the actual software component of the software product line. So if you develop your feature model in pure variant and go all the way into your solution domain and select your product and develop the variability, on your SPL, then it will help you by developing hierarchical tree-like model. And this model consists of components, and these components are implemented with either one or more feature. And then the feature model, you will be able to see the code of that feature model. So now you have one-to-one mapping between the source code and the feature, and then you can understand the whole connection, and then it's easier for you to modify and change. And even for testability, it will be great because you can test these specific codes instead of going all over the yard and test everything. So you can see traceability is a tool that enables us to monitor, isolate, understand, design, redesign, control our variability decisions and commonality decisions, be able to move from solution domain to problem domain and back and forth, so we can really control the whole situation and bring discipline to the development process. And especially, we're going to talk about this later, using agile processes. As you know, it's all incremental. And if you are doing design by incremental cycles like sprints, you need to be able to isolate and work your sprint separately, test your sprint separately, deliver your sprint. You don't do it for the whole system. And therefore, traceability is very valuable in this sense. This leads us to what I was talking about now, which is the Devops as a design framework for agility in the software development process. We always talk about continuous delivery and deployment, which we just say CD. The CD design calls for different techniques and practices that designers and developers should follow to make sure that they are following a design procedure that would make it easier to implement DevOps, which means continuous delivery, continuous deployment. It is important to understand how an application should be re-architected to support development operations. We know that there is resistance, especially in big traditional companies, to follow this technique because they are always focused on deadlines, budget, and clients. That's the most important thing in their life. So if you tell them, well, we are going to develop it in incrementals, we are going to develop it in pieces, we're going to involve everybody. Even the issue of involving everybody here, from customer end to design and coding, is making them nervous because these are large organizations. And to put small teams together to develop design stages is extremely difficult because they are not used to that. But we are going to talk about some companies doing this and what results they have achieved. It's a change in paradigm of allowing huge development processes to be taken by 100 teams. And these 100 teams collaborate on daily basis and communicate. It's not easy. But is this a better way or the old way, by just getting the whole company involved in developing something stage after stage, and no stage talk to the other, and there is no back loops, and you have to keep going till the customer receives the product. So in some research, I'm referring to it here, there is a conceptual framework being developed to support this architectural process that will support continuous delivery under DevOps. They just talked about design patterns, attributes, and how you should use them to the advantage so that you can deliver a design methodology that is friendly and promoting DevOps and continuous delivery. This is what they are talking about. This here shows the continuous delivery for DevOps. For example, you see in this table that these are the characteristics of, or if you will, the attributes or some people call them non-functional requirements, or design patterns, whatever you want to call them. These are, if you want to promote deployability, or you want to develop, promote automation, or you want to do traceability, like we talked about, loose coupling. These are lots of researchers here quoted that have addressed these issues in their papers, and we investigated these ones, how to promote loose coupling in your software product line so that it will be compatible with DevOps and help you to do continuous design, delivery, and deployment. So this is a research area that is wide open. You can see here in this last slide that by re-architecting, by doing the re-architecture of your quality attributes here, the quality attributes of like traceability, deployability, and all that, if you do look at them from architectural point of view, you can promote DevOps and continuous delivery practice by looking at this. For example, if you want to promote traceability, here it says how to achieve it. Here it says improve test quality. We talked about testing. And here it says making code more testable. And in the paper, if you can read it, it will explain to you how these things are achieved. And then they develop a case study to tell you once these are implemented, this model is implemented. This model has more features than what I'm saying here, but I'm just giving you an idea of how you as a designer should be aware when your design goes to real life under development, and the company has adopted DevOps as a design methodology and process, then you have to be aware that development cycles are short, and they are done in sprints, and they are done in groups, and they have to do the daily sprint, and they have to do all these issues and the testing, continuous testing. Nobody wait till the system is delivered and then get tested, and so on. So with this, I think this is the last, yes. Let's see if there are more questions. Okay, please check the chat more often in the future. It feels as if there is no point in asking questions if they are left unanswered. I really was trying to check, and I asked here, there was a question here. I wanted more elaboration on it. I asked my question about an hour ago. Yeah, I looked at that before the break, and I said we'll handle it, and I need just more elaboration on this question. I don't know if the person can speak out. There's no problem. I think you are not muted. I hope so. Ask more question about an hour ago. I'm sorry for that. Please check the chat. All right, we do. Could you make a quick summary again of the definition of DevOps? Okay, I'll do that. In design, development and operation, which is called DevOps, is a software development framework, let's say, or a practice that promote agility in the design. And in that sense, it follows the agility protocol. It means continuous delivery and development, which means if you have to have continuous delivery and development, you have to have continuous testing and verification. And these developments are happening in a cycle. Sometimes we call it a sprint. It depends on the company. And these sprints goes into like 2 weeks or 4 weeks. You have to develop certain functionality that fulfill a larger system. So you decompose yourself. And this is how you see modularity will help you. Let's say your system has 50 modules to complete, and they are decoupled. That means they can be developed separately. Then you take these modules and put them into sprint or user case or user story, if you will. And then from there, you go into the development process. and developing everything all the way, let's say the features and the codes, and then you do the testing, then you do the verification, and then you declare that this is done. So you get it away from your cycle, and then you continue developing other modules, and maybe at one stage you will sum and do the integration. Now, one thing important, maybe I haven't mentioned more about this, why we are talking about this agile and DevOps, because in the research community, there is a debate saying that all this nice talk about requirements and architecture and design is in violation of agility or DevOps, because they believe you do not design the whole system in its totality at the beginning, and then you go into phases. This is like waterfall design, straightforward, and it fails because you have to go back. You have to go redesign, change requirements, and even requirements. You have stakeholders in today's complex life that are dynamic. They cannot just give you a static document called requirement, and then you go after 3-4 months, come back to them with the design. This is not how it is done in the real world. Stakeholders can change things on you, even in the last stage. But agility, when you use these small sprints and design, you open the door for your stakeholders to change. They can, because you are doing continuous testing, delivery, and change. You are more dynamic, more flexible, doing things in smaller chunks. You don't have to have the whole requirements collected. Once one feature or module is complete in its requirement capture, you can go and work while other teams are working on requirement for, let's say, model 5, model 9, 2 is already delivered, and 1, stuff like this. So in DevOps, it helps you to do continuous delivery, continuous deployment, continuous testing, even continuous elicitation of requirements. And that's what more companies are moving to. And in the last 5 years, we see mega companies, the big dinosaurs, start to feel the pressure that they need to go and follow also the agility movement, even if they are developing legacy systems and large systems. I hope I elaborated a little bit on. There is another course I'll be teaching about agility this spring, and it will go into much more details on this regard. Any questions, please? We still have maybe 4 minutes, or we'll let you go earlier. Okay, no more questions. The following lecture will be about Modularity 2, and we're gonna touch on different subjects and talk in more details about the robot modularity and other related things that may be closer to your assignment. I'd like to thank you. My apology if the questions and the flow of the lecture were not in much sync. But please, when you ask your question, I would really appreciate it if you refer to the point where your question is coming from. Maybe if you mention the slide number or the subject that you are asking about, so we can give you a proper answer on it. Thanks a lot. I appreciate your time, and I hope we got the benefit of this lecture. Thank you very much. See you later.